Hello everyone, my name is Mihaiescu. I'm a cloud architect with Ontario Institute for Cancer Research in Canada, and I'm going to be talking today about Cancer Genome Collaboratory. OICR, or Ontario Institute for Cancer Research, is the largest cancer research institute in Canada. It's one of the largest in the world. Located in Toronto, it supports about 1,700 researchers, and it also hosts the secretariat for the ICGC, which is the International Cancer Genome Consortium, which is a voluntary organization created with the goal of collecting 500 normal tumor samples from the 50 most common types of cancer. There are 17 or 18 countries that participate in this project voluntarily, and they basically collect DNA samples from their cancer patients, and we align them and sequencing them and, with the same algorithms in order to get some good conclusions about the causes of the mutations. Cancer Genome Collaboratory project was created based on a fund by Government of Canada with the goal of providing an environment for the analysis of this data. So researchers normally will have to download the data into their own environments, which means it takes time, it takes space in their environments, and it stops them from doing the research faster. So we have the data in Cancer Collaboratory, we have the compute capacity. It's easier for them to just get an account and do the analysis in the same place where the data is. The genomic workloads are a little bit different than regular cloud-based workloads in the sense that they are not very latency intensive, but they totally saturate the resources given. So CPU oversubscription is not something that you should do in cancer or in genomics-based clouds. And we have plenty of local disk space, allowing the VMs to use the local disk in the compute nodes instead of using any kind of shared resources. The high-level architecture for this environment is basically using high-density compute chassis. We have 16 compute chassis in just 8 U of space in the rack. The rest of the space is used for very large storage nodes, 4U chassis with 36 drives. This allows us to basically saturate the space, use all the space in the rack, use all the ports on the 10 gig switch, and have very good upstream connectivity from rack to rack using the 240 gigabits per second links, uplinks. Having a mix of compute and storage in the same rack allows us to also lower the power requirements. Okay? And if we lose a rack, we don't lose a lot of compute or a lot of storage. We lose just a mix of two, but in a smaller portion. A rack full of this compute chassis would also draw too much power and generate too much heat to be a feasible solution. For the controllers, we are using a pretty standard, highly available architecture with 3 controllers. What we do different here is that we have dedicated RAID 1 SSD containers. So the MySQL has dedicated space and IOPS. Ceph Mon, used by Ceph, also has its own container. MongoDB, the same. The controllers have 40 gigabits per second connectivity in active-active bonding. We use Neutron plus GRE. We have public IP addresses available to researchers so they can use the environment, assign floating IPs as they would do it in Amazon or anywhere else. We are trying to make it as easy as possible for them to consume the resources. Compute nodes, as I said, high-density chassis. We have 6 2-terabyte drives in RAID 10, so we have about 5.3 terabytes usable on each compute node. So the VMs, basically, when they start, they have enough CPU and memory and local disk to do the analysis. Okay? And if we lose a compute node, you only lose a few VMs, which doesn't impact the general workflow. The samples that were analyzed there can be restarted on other VMs. The Ceph OSD nodes, again, we are not using journaling on SSD because they don't help for our use case. We have a read-based workload, and the reads come directly from the primary replica stored on the spindle anyway. And they would take about 20% of capacity just for caching the writes. The storage nodes have 40 gigs connectivity, 20 for Ceph public, 20 for replication. Networking, we use Brocade switches, top of rack. They have a nice ring stack feature that allows you to have basically non-blocking ports in a ring. So if you lose 3 cables going from rack 3 to rack 4, traffic can still pass on the other side. And they use very inexpensive TUNAX cables, so no need for optics. We are totally using open source software, so OpenStack Liberty, Ceph Hammer, Ubuntu, Ansible for configuration management, Zabbix. We monitor probably 30,000 metrics for the entire environment. We have hourly rally tests that do end-to-end testing, as well as tests that download large files and check its integrity to make sure that the Ceph cluster didn't cause any data corruption, and also gives us a point in time on the performance of the object storage service. We also developed a custom client that allows us to give access to the data in the private buckets without giving access to users to those buckets. Basically, we create temporary URLs on demand for the users, so they can download directly the data without having permanent access to it. And also has some nice features like BAM slicing, allowing a researcher to just request a portion of the DNA, like 1 or 2 chromosomes, instead of requesting the entire file, which can be 150 gigs. The cloud usage, we are in the closed beta phase, meaning that only a few research labs have accounts, but even with this limited user base, we had 5,000 instances in the last 3 months, because have users that download the data, run some analysis for a few days or hours, and then terminate the instance and repeat. We have almost 500 terabytes of protected data stored in Ceph, which means 1.5 petabytes, because we use triple replicated pools. And I would like to thank our funding agencies for providing the fund for this project. Thank you very much.